Welcome to the last colloquium of this term. So today we will be delighted to have Dr. Hannah Wakeford. She did his PhD in Exeter University. Then she moved to do a postdoc at the NASA Goddard Space Flight Center. And then she became a Giacconi Prize Fellow in the Space Telescope Science Institute. And she won many, many prizes. I won't have time for them all. I will just mention the recent one. So that will be the NASA Exoplanet ExoGuide. So Hannah, please take the stage.
Thank you, and thank you for the invite to come and talk to you today about some of the work that we've been doing, looking at exoplanets and trying to understand more about their nature and environments. And the thing is, I always like to start by looking a little bit about the history of exoplanet discovery, and there's no better place to do that than here. So exoplanets are not new in thought. So all the way back in ancient Greece, there's writing from Epicurus, which states that there is an infinite number of worlds, both like and unlike our own. But of course, it takes a really long time to realize what that means and the potential of that. And actually, it isn't until we get to the 1600s when we're actually able to start making measurements of our solar system that we can understand the techniques that we might start to be using to do that. And then in the 1850s, getting the first scientific paper claiming the detection of an exoplanet, it turns out to be a binary star, and we discover that stars don't go around on their own. They actually can go around in groups even. But it isn't until the 1980s that we get the first evidence that planets can form and exist outside of our solar system, which is absolutely mind-blowing. It's an incredibly recent discovery in terms of the empirical evidence behind planets beyond our solar system. And then, of course, we get our 1995, the first actual real discovery of an exoplanet around a sun-like star. These worlds actually exist, but they're very, very different than our own. And there's a number of different techniques that start coming in from those radial velocities very early on, to the transit method, the direct imaging of exoplanets, and then it really is the boom of the survey era. How can we now capitalize on this? We know what to look for and we know how to do it. How can we really maximize the information content that we're getting? And Kepler really helped define that demographics era, that ability to understand the prevalence of planets beyond our own, and an idea of what they're like. But it was with the Hubble Space Telescope that we first started trying to look into these individual planets and understand the nature of their environments and their atmospheres. And then in 2021, JWST was launched, and our science on that began in 2022. And I'm going to take you through that kind of discovery and what we've learned with JWST since then, but how it fits into that bigger picture as well. I also like to show the kind of position of these planets across our sky. So in the background, you've got a Gaia image, and then on top of that, each of those dots represents a star, where the color of that dot is the temperature of that star. Each of those have one or more planets around them. They are in every direction you look in the night sky. Planets are absolutely everywhere. There are more planets than there are stars, and there are more stars than grains of sand on the Earth. So there are planets absolutely everywhere. And what I particularly love is the footprint of the Kepler Space Telescope that you can see on the exoplanet discoveries in the sky. Because there are gaps between those CCDs, and therefore we can't see those stars. It doesn't mean the planets aren't there. It just means we didn't look at them. So it's really, really interesting that you can see the imprint of different observation techniques on where we're finding those planets as well. So there's a huge observational bias just imprinted into what we're discovering and learning. One of the key things that often shocks people who don't work in this is that these planets are really close to us. These are our local neighborhood. This is just showing you the distance of those planets relative to the sun. And that Kepler field is actually looking at a narrow, deep field, so it's looking further away at fainter targets. But a majority of these planets are discovered very, very close to the sun. And the importance of that is that means we're looking at relatively bright targets. And if we've got relatively bright targets, it means that we can get the signal to noise to be able to measure more about these planets and learn more about their characteristics. Now, to look at the atmospheres, the key characteristics that we need first order are their mass and their radius and their orbital period. And what I like to do with these two figures side by side is you often see these kind of demographic figures for exoplanets, but putting them side by side shows you that these planets are both like and unlike our solar system worlds. So when we're looking at them in terms of their period, so their distance from their star, they're very unlike our solar system. And this is absolutely filled with observational bias. It's easier for us to detect things that are close to their star. It doesn't take as long for them to orbit, so it doesn't take as long for them to impart that radial velocity signal so we can calculate their mass. It doesn't take as long for them to pass in front of their star, blocking out some of that light so we can get repeat measurements of that. So there's a huge amount of ease in finding these shorter period planets. But the fact that they exist at all is already an interesting part of that discovery space. But then when we look at it in terms of the density, so when we look at it in terms of our radius versus mass, they suddenly look very much like our solar system planets. So we've got to ask the question is, are these planets just a transplant of our solar system into a different environment? And how is that environment changing the nature of those worlds? I've highlighted on here the darker histograms and the ones with the black circles. Those are all our giant planets. Those all have a radius which is larger than Neptune. They are almost certainly contain a significant amount of hydrogen and helium in their atmosphere. Those are the ones that I'm really interested in. I'm going to focus on in this talk, although there is so much stuff to learn about these smaller worlds as well. What we want to do with this is really get a deep understanding of what it means to be a planet. So one of the things that we're trying to do is we're trying to construct this comprehensive library of spectra of these different atmospheres, these different environments, so that we can really critically test and understand the roles of chemistry and physics in their atmosphere. How does the dynamics play with the chemistry in the atmosphere? How is that tied to the temperature and the nature of the star that that planet is orbiting? We've got all of these different parameters that really matter in changing the environment of a planet. How can we build up a library that allows us to reference that so that when we find a new planet, we can place it within the context of these global trends that we're trying to realize? One of the things that's really important that we haven't been able to look at until very recently is that these planets are multi-dimensional objects. They're three-dimensional, and if we're lucky, we might even be able to find out that they're four-dimensional and change with time, only if we're lucky. So this multi-dimensional world, we can now start trying to pick that apart and understand and map how the structure in this one planet is actually affecting what we're seeing when we get this global one-dimensional average of it. And fundamentally, what we're trying to really understand with all of these different test tubes, of all of these different hundreds, thousands of exoplanets, is how does that all tie back to its formation? How does that tie back to the origins of planets? How can we use these other worlds to understand more about the presence of our own? So the method that I use to do this is called the transit method. So a lot of you will be familiar with this. And what we're doing is we're looking at that planet as it passes in front of the star from our point of view. And as it does this, it blocks out a very small amount of that light. And we can measure that change in the amount of light. And if we do that as a function of wavelength, we can build up a picture of what that atmosphere is made of, because the different atoms and molecules filter the light in a different way. If they're aligned in such a way that we can also get the eclipse of the planet, so when it passes behind the star and is completely blocked, so now we're just looking at the star itself, all of the light from that system is just from the star, we can do a subtraction and get an idea of how much light added together the star plus planet gives us by the amount of flux we're getting before and after it disappears. So in this eclipse, we're actually able to measure the brightness, the emission from that planet itself, and get an idea of the thermal temperature of that planet's atmosphere. So combined, we can get really detailed information about what's going on in this planet's atmosphere from its day side to its night side. And now I say from its day side to its night side because these planets are these hot Jupiters. They're those ones that were the giant planets in the top corner of that figure. They're very close to their star. So many of them orbit within 10 days. And at this point, they're tidally locked to their star. That means that their rotation period matches their orbital period, and they have a permanent day side facing the star and a permanent night side facing into space. So because of this, you have this very intrinsic dynamical structure which is put in there. You've got radiation coming in from one side, which is driving supersonic winds around the planet in a jet that stretches over many, many latitudes. So from this, we can actually start picking apart the drivers of those and how strong those winds are, which tells you something about the way in which that atmosphere is reacting to that radiation environment. And the key thing is that this transit is actually imprinted with information on the temperature and the gravity and the mean molecular weight of that atmosphere. So the measurements that we're making are dependent on the scale height of the atmosphere. So the scale height for these hot Jupiters can be in the hundreds to thousands of kilometers. Compared to our solar system, Jupiter has a scale height of about 25 kilometers. The Earth's is 8. So these are incredibly inflated atmospheres, very low density extended atmospheres, where we can get lots of light shining through them so we can pick up that information much, much easier. In the emission, it's really dependent on that thermal temperature. It's the black body radiation that we're measuring. And then what we're seeing is deviations from that black body so that we can work out what on the day side is emitting or absorbing some of that radiation. So that temperature of our planet, these hot Jupiters, being so close to their star, are actually in the thousands of Kelvin. So the one that I'm going to be talking about today is 1,700 Kelvin. So the black body radiation is peaking in the infrared. So we can use this information so that we can build up a better picture of what is happening in these different environments. And to show you, to give you an idea of what we're seeing when we're getting these spectra, it's the opposite of what you get when you're talking about an absorption spectra in the lab. When you're talking about an absorption spectra, you see a dip because you're blocking some of the light. Now imagine that absorbing material is in an annulus around our planet and then it's blocking a light source, our star. Because it's blocking the light, our planet actually appears bigger. So when we're seeing an absorption feature in transit spectroscopy, we actually see a bump. We don't see a dip because what we're measuring is the size of the planet getting bigger as the atmosphere blocks more light. So everything's flipped from what you might normally see. So we can start with a baseline atmosphere for these planets. They're giant hydrogen-helium worlds. We've got hydrogen, hydrogen, and hydrogen-helium collision-induced absorption, which imprints its own signature on the light that we shine through it. We can build on top of that our water vapor. This is not liquid water. This is steam. This is gas, because we're again at those very high temperatures. And we know from just looking at the Earth's atmosphere, water is a beautiful infrared absorber. It absorbs in lots and lots of different bands across the infrared. You can see the classical JHK gaps in the bands here, which we use to look through the Earth's atmosphere. But you can see that water absorption coming in on top of that feature. We can also look for carbon-based species. So the carbon molecule CO2 is that really big spike there with the small movements from the CO added in there. So the carbon species are predominantly in that further infrared range. And then we can look in the optical at our atomic species, so our sodium and our potassium, and you can see that those are really impacting our optical portion of the spectrum. So we've got all of these different parts of the spectrum that we need to be looking at to build up an understanding of the different components that go into our atmosphere. And to kind of show you what that looks like, here is just a breakdown of a number of different species for a particular pressure level, for a particular amount of metallicity, so how abundant these different materials are, for a particular temperature. And you can see we've got all of these different species, again, building on top of each other, where we're looking for these absorption signatures. And one thing to note is that the Hubble Space Telescope has been a real good workhorse in us finding and discovering the atmospheres of some of these giant planets. But it's very limited in its wavelength range to the optical and then the near infrared. So it's able to capture that sodium-potassium spike, which you can see in here. So that's the red line, and then that big gray line, that's our potassium. But it's unable to capture any of that carbon species. So for a decade, we've been using the Hubble Space Telescope to characterize these worlds, but we've been limited in what we can tell you about those worlds. So that is why the JWST Space Telescope is so important in what we can understand, because we've now got access to more of that chemical inventory, because when we build up that picture, we can get an understanding of those questions I asked. What is the formation mechanisms for these? How can we tie everything together? What is the environment of these worlds like? And that's going to be the balance of the water versus the CO2 versus the CO and the methane, and how does that all come together? So with the Hubble Space Telescope, we've actually done a huge amount of groundwork. And what I'm showing you here is that mass radius diagram again, but now I've put on top of it just some slides of the detections that we made over a decade worth of observations that had been done. And this is from the very, very smallest planets over here. These are, you should all be very familiar with the TRAPPIST-1 planetary system, to some of the largest planets that we're looking at. And one of the key things that we were looking for was that near-infrared absorption of water vapor. And what we found is that there is water vapor in about 80% of the planets that we have looked at. And that's measurable water vapor. That's not saying that it's not there in the other ones, it's just that we weren't able to measure it. But one of the key things that this histogram is showing you, which is showing you the amplitude of that water absorption feature that we measured in each of those planets, is that we were often seeing that it was muted to about a third of what we expected, of what we predicted that absorption feature should look like. So just to show you what that looks like on a model, here's just a toy simple model. So this is our nominal atmosphere that we would expect to be measuring for one of our hot Jupiters. And the question is, if we're measuring an absorption feature for our water with the Hubble Space Telescope, so it's just these first two water absorption bands here that is smaller than that, is it because there's less water overall, or is there something else in the atmosphere blocking the light? This is where I start to get really excited, because this is where we start looking at different opacity sources and asking the question, what could change the amplitude of those absorption features? And the easiest and simplest solution for that is something we're very familiar with here in Britain. It is clouds. If we stick a cloud in this atmosphere, so if we stick some kind of solid or liquid particle suspended in a gas, that's what our cloud is. If we stick that in the atmosphere, it's going to block or scatter that light in a very characteristic way. If you have large particles, you end up with uniform scattering of all wavelengths. So you end up with white, which is essentially what our water clouds do. They're bright white. That's because they're blocking that light. They're scattering it on all of those different wavelengths. But if you have very tiny particles, you end up with this very, very strong enhanced scattering in the blue. So now we can see in our water absorption feature that our clouds, putting different clouds in there, somewhere between these two kinds of models, changes the amplitude of the water that we're going to be measuring with the Hubble Space Telescope. But one of the key things is we're using that gas, we're using that measurement of water to tell us how much oxygen is in this atmosphere, how much oxygen was delivered to this planet when it was forming, So that can tell us a little bit more about potentially where it formed in the first place. So if we're measuring less than we thought, because there are clouds in the atmosphere, we're getting our interpretation wrong. One of the good things is that these clouds impact the infrared portion of the spectrum less. So we have much better ability to measure those molecular absorption features from the gases in the infrared where the clouds have a smaller impact in the atmosphere. So JWST is perfect for us being able to look at these molecular absorption features, not just adding in that carbon and the sulfur species and various other stuff, but also allowing us to break that degeneracy between these cloud opacities, which are telling us that the abundances of materials are different than what we expect. That's what everybody kind of has on the clouds are rubbish and we hate them negative side of things. Get them out of the way, we just need to go to the infrared. I love clouds and I think that they're fascinating. So I actually want to learn about the clouds themselves. So one of the things that you might notice from this is that we can actually use that optical data to tell us a little bit more about the clouds. Small particles scatter the light, large particles cause uniform opacity. So can we use the scattering to understand more about what these clouds are actually like? So one of my PhD students, who was then my master's students, went off and did a retrieval analysis. So this is an inverse Bayesian analysis where we take the data and we ask loads of models to try and fit to that data. And we get a statistical understanding of how well that model is fitting. And what we did is we took a whole load of data sets and we asked the question, what would happen is if we just modeled the infrared part of the spectrum? What answer do we get? What then happens if we increase the wavelength coverage and include more data, and then more data and more data? What information changes when we do that? What do we learn by increasing the wavelength coverage? And what you can see on the side here is the information content that you gain or lose, so the change in our information content between including more data in your analysis. So if you include the optical data in your analysis, which is beyond the reach of JWST, we're actually getting more information on the clouds themselves. So we can break that down further by asking what information is it giving us. And predominantly what we found is that the Hubble wavelengths are really important for giving us an idea of that scattering slope and therefore the sizes of the particles that are in the atmosphere causing this opacity source. Now we've taken this a step further and I've got a large program on the Hubble Space Telescope called HUSTLE, and we're looking at 16 different exoplanets and we're measuring them across the UV to optical spectrum. And what we're trying to do from this population study is look at that scattering slope across all of these different temperatures, where we can see you've got these different domains that we expect to have. So our gas domain, everything's a vapor, there shouldn't be any solid or liquid particles. Into our dissociated domain, where H- is going to be dominant in that portion of the spectrum, to our condensates and our hazes, so these photochemically generated materials, and trying to look at that population and understand how we can use that scattering slope to get a better information on what types of clouds are forming in these atmospheres. But we can go down to kind of the simple theoretical tests. We can ask ourselves, what should these clouds be like? We can start by looking at the temperature, and we can look at our solar system. What you're seeing here is the temperature pressure structure of our solar system planets. So along the bottom is the changing temperature, and then along the side as we go up in altitude. So how does the temperature change as we go up in altitude through these planetary atmospheres? And what you can see from those dashed lines is the condensation lines. This tells you when you reach 100% saturation of that material, you should potentially be forming a cloud of that material. So it should be forming a liquid or a solid. So for our solar system, you've got things that we're very familiar with, like the methane clouds, the ammonia clouds, and the water clouds. But when we look at these giant planets that are incredibly hot, we enter a completely different regime of what their clouds are going to be made of. Instead, we've got our temperature pressure profiles, which are crossing lines which are made of sulfur-bearing species, sand and glass, iron, and corundums, which are rubies and sapphires. So the clouds that are making up these atmospheres that are blocking those gas absorption features are made of rocks that we're standing on. So how can we use that information to understand more about these planets? How does that change the way in which we can view them? A lot of these materials, you'll notice, contain a huge amount of oxygen in them. Magnesium silicate can contain 4 oxygens when it's forming. So the oxygen depletion due to the formation of that cloud means that our water is intrinsically going to be different as well. So the formation of the cloud itself is going to change the chemical inventory of the planetary atmosphere. So without knowing what those clouds are made of, we can't actually tell you how much water, how much oxygen there is. So now we've come to the point where we know we've got clouds. We know if we go into the infrared, we can get a better picture of the gas phase chemistry. But now we know that the clouds are going to be taking up some of that material as well, and that's going to affect the measurements that we're making. The wonderful thing is that nature provided us with the fact that every atom and molecule absorbs light in a different way. It interacts with light in a different way. And these minerals are molecules, so they're no different than anything else. The only thing is, their absorption features are much further into the infrared. So now we need to go into the mid-infrared wavelengths to see any of these absorption features, which are known as vibrational modes, to actually identify what those clouds are made of. What you'll notice from this is that the scattering slope for a lot of these is very similar. So the particle sizes and the scattering slope are degenerate with what the material is making that cloud. So only when we go and actually measure the individual absorption features can we tell you how much oxygen is likely locked up in those cloud species. We can go back to our toy models on here, and we've got our 3 different cloud species. And now if we just model a very simple small particle cloud made of magnesium silicate, so sand, what you end up with is this absorption feature in the mid-infrared above the gas phase chemistry that we should be able to measure to identify what that cloud is made of. So we've got the scattering slope in the optical, which can tell us our particle sizes, and we've got our absorption feature, which we can go away and measure so that we can understand these planets. Because what we're trying to do is trying to get a better idea of what these worlds are like. I can show you this in a GIF form because everybody loves moving GIFs. This is showing you what that magnesium silicate, if you change the abundance, so you change the amount of magnesium silicate you've got, and what you're seeing is how those absorption features change in these 2 different wavelength regions, and how in the middle, it doesn't care. It's not affecting that middle part of the spectrum. So it really is the optical and the mid-infrared that tells you about the clouds, but that beautifully leaves this middle part of the spectrum where you can get the gas phase chemistry separate from that. So we can now get an idea of how the clouds are interacting, but we can also measure the gases in these planetary atmospheres. And if we bring everything that we know together, the particle sizes, the temperature, the physical properties of our atmospheres, and the availability of those materials, these aren't all sun-like stars. What's the star's metallicity? How much oxygen does the star have? How much carbon does the star have? The availability of material is also a really important aspect in trying to understand the relative nature of these planets in their own environments. One of the key things is combining everything together. And that's not easy to do. 1, we don't have patience. 2, we don't have money. And 3, we don't have time. So there's so much information we need to combine together to piece this puzzle in place. It actually takes a lot of detailed observations to track down these dynamical and chemical processes. So enter my case study for you. This is WASP-17. We're going to be looking at it in detail. And this is work done from the deep reconnaissance of exoplanet atmospheres through multi-instrument spectroscopy, the DREAMS program. Our DREAMS program is a GTO program on JWST. It's part of the JWST Telescope Science team. This is the STSCI team run by Matt Mountain. You can see the names of all of our team here on the Transiting Exoplanet DREAMS side. We have 130 hours of guaranteed time on JWST in the first year of operations. What we did with that 130 hours of time is we tried to design a program that you would never get through normally. You'd never get someone to give you this much time to do something that seems mundane. So what we did is we designed 3 different programs. 1, a deep dive into a hot Jupiter's atmosphere. 2, a deep dive into a warm Neptune's atmosphere. And 3, a deep dive into a terrestrial planet's atmosphere. In particular, what we're trying to do is build up a huge library of information for these planets. We want a complete spectrum from the optical to the mid-infrared. And we're doing that in both transmission and emission for our giant planets. And we're doing that in the full wavelength availability for transmission for our rocky planet. I'm going to focus on our large program for WASP-17b and show you the power of information that we can get from dedicating this much time and wavelength coverage to a single planet. So, a little bit of a history on WASP-17. What do we know? What do we know about WASP-17? Well, it is an inflated hot Jupiter, so it's a very low density. It's about half the mass of Jupiter, but about twice the radius. So it's an incredibly puffy planet. It's about 1700 Kelvin, like I told you before, and it orbits in about 4 days around its star. So this is a hot Jupiter. It is tidally locked to its star. It has a permanent day side and a permanent night side. Previous observations from Hubble and Spitzer have given us information on the transmission. So we have about 7, some not so good, observations with the Hubble Space Telescope and 2 with Spitzer Space Telescope. And then in emission, all we had was cold Spitzer observations, which were looking in 2 wavelength bands, so 2 photometric bands, and we got 2 observations of those. Now, from all of those observations, what we were able to analyze is that we can't really learn too much. What we learned was there's water in the atmosphere and there's CO2 in the atmosphere. We don't know how much. There are clouds in the atmosphere. They're scattering, but we're really not sure how they're affecting the data. What we found when we fit all of this data, and this is work that was done by my then PhD student, Lily Alderson, is that we end up with a bimodal solution in all of our abundances. So that means it could either be subsolar or supersolar, or somewhere in between. So this led us to ask the question, what can we learn? What are we going to be able to solve with this JWST program? The first thing we're going to be able to solve is to get rid of these hideous transits. So these are gappy because Hubble is in orbit around the Earth. Every 45 minutes it gets blocked by our own planet. So there's literally a gap in our observations. We make shit up in between. The Spitzer one is very, very low precision. So how can we improve on that? Well, JWST did it automatically. We spent 74 hours on 3 eclipses and 3 transits from 0.6 microns to 12 microns, and we had, straight off the bat, outstanding precision. We made sure to pair up our transit and eclipses so that our transit was observed, and then immediately, half an orbit later, our eclipse was observed, pairing up our observations in each of the modes. what we saw from the raw data, uncorrected, unfitted data, is these. This is our eclipse, this is our transit. As we build up the spectrum, going to longer and longer wavelengths, we can actually already, just by eye, tell you stuff that's happening. In the transits, you can see that we're going from a quite curved bottom here from our transit to a fairly flat bottom. That's telling you about the limb darkening of the star. The star gets darker as you go towards the limb, and we can literally see the impact of that by eye. Not even corrected data. In the emission, what's beautiful that you can see by eye is the black body of the planet itself. What you're seeing is you go from the shortest wavelengths in blue, so from our top left corner down to our bottom right, we're increasing our wavelength. You can see the eclipse getting deeper and then shallower again. We've hit the peak of our black body of our planet, and we can tell you that by eye. Unbelievable precision. So it won't shock you to know that the information content in these data sets is immense. And I'm just going to take you through a small portion of what we've done so far with these data. And I'm going to talk in specifically about these 6 papers that we're working on and have already published 4 of them. And then I'm going to talk to you about how we're taking that further so that we can realize these planets in multiple dimensions. So, spoiler alert, there'll be a lot of spoilers on these slides. These are going to be on places where we've got unpublished work, but please do enjoy with your eyes. We've got this amazing transmission and emission spectrum for this planet that is telling us a huge amount about what's going on in this atmosphere. So let me take you through that transit and then the eclipse and further through. The first observations that we actually published were some that I found the most exciting. And I've already kind of told you what that's going to be related to. It's actually the discovery of these clouds in this planet's atmosphere. What we did is we looked in those Miri wavelengths that I was talking to you about, and we saw something we didn't expect. We were expecting to see some magnesium silicates, a broad feature like the purple line I showed you before. Instead, what we saw was quite a narrow, spiked feature in our spectrum. And we had to go off and take all the models that I'd made and apply lots of different materials to it to figure out what was going on here. And what it turned out is that this data is showing you that the clouds in WASP-17's atmosphere are made of quartz, silicon dioxide. So it's like a clear white crystal that you get in all of the rocks on Earth. And we were able to show that because we combined our information from the JWST with the Hubble Space Telescope, again combining that power of that scattering slope and our absorption feature to get an idea that these crystals were about 10 nanometers in size. They were at about 0.1 millibar pressures in the atmosphere, so high up in the atmosphere. And this is telling us that we've got some mechanism in the atmosphere that is lofting material continuously high up in the atmosphere, creating these small particles. So we've got some dynamical information imprinted on the presence of these tiny crystals which are flying around this planet's atmosphere. Again, I bring home the point with these 2 different GIFs. Now we're looking specifically at that quartz feature. We're changing in this side, we're changing the amount of quartz that we have in the atmosphere, and on this side, we're changing the size of the crystals of that quartz. And you can see the 2 very different ways in which they change how that spectrum is going to look for that planet. But critically, you can only do this with our optical and our mid-infrared data. If you just have that near-infrared data, you're not going to be able to tell what those clouds are doing. So to get that information on that oxygen, so our silicon dioxide is just taking 2 oxygens, we needed to have that mid-infrared information. But there was so many improvements to make in the optical. I already told you that we had this bimodal solution from our transmission spectrum from Hubble. We weren't able to tell you what the water abundance was. So our new observations from JWST actually filled in that gap beautifully. What you're seeing here in those blue and green color points is our JWST measurements of this planet's atmosphere. And when we combine that information with what we already have, we were actually able to now tell you that that bimodal solution, we should be in the supersolar part of that. There was a solution that was subsolar, there was a solution that was supersolar. And we've got a really nice, clear detection of that water abundance now because we've got such a huge wavelength coverage that we're looking at. So all of these bumps are our water absorption features. One of the other key things that we saw is that there is also likely the presence of H-, so dissociation of water. So the water is being broken apart, likely on the day side, where it's heated and being transported to the night side of the planet. So we've got this water cycle, which is occurring in this planet's atmosphere, where the water being transported in the atmosphere is being dissociated, transported, reforming, and then being transported around to the day side again. One of the really important things for this SOS observations, and I put this up here because just to show you how hideous the data we're dealing with is, and if Madhu's shown you any of his, it will look like these bananas as well. The SOS data is a slitless spectrograph. It causes this curved shape to it, but it also means that any nearby stars are contaminating your spectra. And WASP-17 is one of the worst contaminated spectra that we have because it's in a crowded field. So you can see all of these chevron-shaped light sources here. Those are all background stars, which are also being illuminated on our detector. So what I'm doing with a machine learning expert at the University of Bristol, she's working on training this algorithm, we're calling exotic clean, to label, extract, and then analyze those images to remove those zeroth order contaminants. And what you can see on the right-hand side here is our first training set cleaning of this WASP-17 data. So you can see that we're removing a large number of those contaminants, but what we've got is a bit more training we need to do on our machine learning algorithm before we can actually remove them completely. But this kind of method for data cleaning is going to be really key so that we can open up the wavelengths and open up the targets that we can look at with these kinds of instruments where we can actually just remove those hideous contaminants. If we bring our transmission spectrum together, this is going to be a paper which is led by Nicole Lewis, who is the PI of our whole 130-hour DREAMS program. And you bringing that together with our near-spec data, so our near-infrared data here, we've got a really clear detection of our carbon dioxide feature. So again, we've got this beautiful constraint on our water and our carbon dioxide, and the scattering that we're seeing from those cloud particles. So when you bring it all together and fit that data, we're getting confirmation of that super solar metallicity in this atmosphere. When it comes to the eclipse, we really didn't have any idea what to expect. So when we're looking at the eclipse, we first saw that we're looking at these very different pressures in the atmosphere. And what we can see is this scattering profile towards the optical, which could either mean that we've got high internal temperatures where we're probing very deep in the atmosphere, or we've got scattering albedo from the clouds that are forming. So we still have some open questions from our first data set as to what's going on. Some of those keys come in later when we look at those longer wavelengths, and this is work that was led by my PhD student, Daniel Valentine, where we're looking at the thermal emission from this planet near the peak of its output. And what we're seeing, this is high up in the atmosphere from eclipse mapping, which is allowing us to actually get a two-dimensional picture of this planet's atmosphere. So how is the heat being transported in latitude and longitude? We can see that we've got a shift in the peak heat of this planet from the substellar point, the point directly underneath that star. So there's transport of heat from that substellar point in this atmosphere, meaning we're getting advection of that material around the planet. And what we actually find from this is we get a temperature contrast from the day side to the night side of about 1,000 Kelvin. If we bring that all together, what we see from our emission spectrum is deviations from a black body. So a black body in this brightness temperature diagram would be a flat line. So you can see it's definitely not a flat line. And that's because we're probing different pressures as a function of wavelength here. But we're also seeing those absorption features from our water and our carbon dioxide again. And we're able to constrain the temperature profile of this planet's atmosphere so we can understand where that information is coming from. So what the different layers of the atmosphere actually look like. So we're now getting pressure information from the measurements that we're making. One of the key things that I told you at the beginning is that we're really aiming to realize these planets in multiple dimensions. So when we take that eclipse mapping and we apply it to all of the different wavelengths, again, work that is now being done currently by my PhD student, is we're looking at these different wavelengths. And what you're seeing is the contribution of the different pressures at those different wavelengths. And if we map that in multiple dimensions, what you're seeing is you're going from those longer wavelengths, relatively high in the atmosphere, where you're seeing a shift of about 18.7 degrees, and then we're going deeper into the atmosphere at our shorter wavelengths, where we're seeing a shift in that hotspot of a much larger degree. And that's because we're probing down to that uniform distribution of heat being transported around the planet. So we're starting to actually build up that three-dimensional picture. We've got these 2D maps, and they're showing us pressure. So we've got these layers in the atmosphere we're actually able to build from the data alone. One of the exciting things that we're doing at the moment with this data is applying a technique that was developed by my then postdoc, David Grant, to use a Fourier series to describe the transmission annulus around the planet. And if we break that up as a function of angle, we can actually try to unroll that and map how the opacity of the atmosphere changes as the planet is passing in front of that star. If we do that, we can start to ask the question of what different things are causing opacity at different points in the atmosphere. One thing that we might expect to be imprinted on the atmosphere is the clouds that I've been talking about. Where are the clouds forming in this atmosphere? How do they change the opacity from one side of the planet to the other? And the thermal scale height. From the day side, you're transporting heated gases. The scale height of the atmosphere is dependent on your temperature. So the hotter gases are going to have a larger extent than the colder gases. So we've got this multidimensional information that should be imprinted on our data. So how can we look for that? So we used this technique and we applied it to all of our transit data. And what we found is that we can see those deviations from a circle. So what we're measuring here, unfolded at the bottom, is the deviations of that planet's opacity as a function of angle around the planet. So deviations from a circular planet. And when we take each of those angles and each of those wavelengths we're looking at, we can actually create a spectrum as a function of angle around the planet. So now we've got 5 different spectra from different angles around the limb of the planet, and we can fit that data. And what we found is that what we're seeing is the hot side is less cloudy and less scattering than the cold side. So there's more scattering as we move towards the morning limb of the planet, which suggests that the clouds are actually forming across the night side of the planet itself. So we've got multiple bits of information here that we can now piece together and ask ourselves what's happening in multiple dimensions spatially on this planet. So when we bring our transit mapping, which is telling us that the clouds are forming across the night side of the planet, with our eclipse mapping, which is telling us that there's a day-to-night temperature contrast of about 1,000 degrees, is we can ask the question of how does that all fit together? And the wonderful thing is that all of that is then, through a third technique, shown to be the same, because what we're doing now is we're taking our transit and we're taking our eclipse, and we're subtracting those so we can get the night side flux. So now we're getting emission from the night side of the planet using a method called the planetary infrared excess. And that third method has given us the same information. We're colder on the night side by about 1,000 degrees than we are on the day side. So we know how the temperature is now changing around this planet from just pairs of eclipses and transits. We didn't need to look at this system for the full 4 days that it orbits around its star. We just needed those 10 hours either side. So let's bring this all together, and I want to also kind of highlight some extra things that we still have yet to learn. And one of the most exciting things is that we just got awarded some more time to look at this planet in cycle 4. And the reason we got that time is because since our discovery of these quartz clouds in the atmosphere, there's been work which has shown that quartz itself has what are known as polymorphs. At different temperatures, the crystal structure changes the way in which the quartz interacts with light. The resolution of our single observations could not tell us which type of quartz was being formed. But with 2 more observations, what we're going to be able to tell you is that the quartz in this planet's atmosphere is formed at a particular temperature. So tridymite versus cristabalite versus beta or alpha quartz all form at different temperatures. If we measure any one of those polymorphs, what we'll be able to tell you is at what temperature did that cloud form at. And that again will give us more information about the dynamical processes that are happening in this atmosphere. The other thing that we're working on at Bristol by my PhD student Matt Lodge is understanding how treating clouds as crystals that have shape and structure compared to spherical droplets, which is me theory and very simple, changes the way in which it should interact with light. So Matt's been working on 2 different codes which allow us to do very fast computations for very specific shapes of fractals and aggregates, which will allow us to actually apply this to these planetary atmospheres. And not only will we be able to tell you what temperature our quartz formed, but we'll be able to tell you what the crystalline shape is. If we bring all of that information on WASP-17 together, what we're seeing is that we've got very strong detections of water and CO2 in the atmosphere, which allow us to really place constraints on the metallicity and C/O ratio. We're getting this superstellar metallicity. It's also supersolar, but what's important, like I was saying with the availability of materials, is that it's superstellar. This is a metal-poor star compared to the sun. So that measurement is really interesting because we're seeing a metal-rich planet around a metal-poor star. The clouds are forming across the night side of the planet, which tells us that there's this temperature mechanism and dynamical mechanism at play. They're small crystals. Something is causing them to be maintained at that altitude. And we're getting this very consistent through multiple methods, day to night temperature contrast, telling us about the relationship between re-radiated energy and transferred, advected radiation. I already told you that there's 6 papers I took you through. I took you through a few more at the end there. This is actually not even now a complete list of all the papers that we're publishing on this single 74-hour program. There is so much information in there that we're learning about this planet. My ultimate goal is to build you a 3-dimensional world based on the data alone. From that, we can really test our models and start to understand what we know about the physics and the chemistry in these alien, exotic environments. And with that, I will take questions.